Hello everyone, my name is Amey Parundekar and this video is about my first digital assignment for computer graphics course in which I'm going to demonstrate how to draw 3D primitives using OpenGL. Now, first of all, I would like to tell you that in this tutorial or in this video, I've used PyOpenGL instead of OpenGL in C++, and a major reason for this was that I had a Linux Manjaro system which has Arch Linux, and I had a really hard time installing GLUT and all the OpenGL libraries that are required for C++, and I really had very difficult time doing that, so I thought I would go with PyOpenGL. So PyOpenGL is basically a Python library that converts all your OpenGL code in the backend to the C or C++ OpenGL code. And in fact, some of the code that we write here has comments which have C code in them or C++ code in them, which is at the backend interpreted as C code through the GLUT or Pygame libraries. So I'll show you what exactly happens. So I hope I have justified my use of PyOpenGL instead of normal C++ OpenGL. It is exactly the same. All the functions, all the libraries and everything work exactly the same. The only difference is that we are coding in Python and we are not coding in C++. That's the only difference. But here also we have object-oriented code, and here also we have the same functions, function names, and hence it does not really make a difference whether I'm using C++ or Python. So with that being said, I am going to start with my basic code, which will show us how to draw shapes using OpenGL. Okay, so if before I start doing that, I should probably tell you how I installed PyOpenGL and what all things are required for get all of this code and up and running on your system. So as you can observe here, I have used virtual environment. I have set up a virtual environment which has PyOpenGL, OpenGL context, NumPy, PyVRML97, and PyDispatcher in it. So this virtual environment has OpenGL context, which provides the overall rendering of the code. PyOpenGL that actually renders the interface, that actually that is what is used to render your 3D graphics and all the crazy things that you will do here. And NumPy is used for arrays. So on your screen right now you can see this array right here which has vertices. So for these kind of things NumPy is used. PyVRML97 provides a VRML97 rendering and scene graph mechanism which is core to OpenGL context, and PyDispatcher provides routing and observation support for PyVRML97. So that's about it. You can install all of this using pip. So pip install virtual env and NumPy, imaging, PyOpenGL, OpenGL context. All of this can be installed using pip, and you can find installation procedure online. So I'll skip through that now and go ahead with my code. So here on your screen you can see basic Python code which is used to draw a triangle and a square using OpenGL. So before going into 3D, I just want to demonstrate what OpenGL can do for us and how it exactly does things. So the first step is basically we define vertex shaders and fragment shaders. So what vertex shaders do is they are going to help you define your vertices, and fragment shaders are going to help you define your colors and all the textures that go behind your shapes. So that's what those two things are going to do. And as you can see here, In fact, in the vertex shaders, we have a shader object with a compile shader function on acting on an object, and inside the function we have passing a comment, and this comment is basically C++ code. This is not Python code, but it is C++ code that we are passing in. This code will be interpreted in the backend using, let's say, glut or some other OpenGL library to and render all of the OpenGL um, code that we have here. So yes, I will go at the top here and explain line by line what exactly happens. So first we do our imports. The OpenGL context testing context allows for the use of Pygame, WX Python or glut GUI systems with the same code. These imports retrieve an appropriate content for this machine. If you have not installed any extra packages such as Pygame or WX Python, this will likely be using glut. So if you don't have glut nor Pygame, this won't work, so you need one of them. So that's what is happening in these imports. Then we also import PyOpenGL, as you can see here, OpenGL.gl import, that is our PyOpenGL import, contains the standard OpenGL function that you can read about in the PyOpenGL man pages. You can go ahead and read them. PyOpenGL array.vbo, this one right here, contains the VBO class, which is a convenience wrapper which makes it easier to use vertex buffer objects from within PyOpenGL. It takes care of determining which implementation to use and the creation of offset of objects and even basic slice based updating of the content in the VBO. So that's what that is basically used for. This is completely analogous to the VBO that you will be using in your C++ OpenGL code, and arrays have been used here, which basically use NumPy in the backend to define all your vertices and edges. Then let me head back to my onInit function. The onInit method is called after there is a valid OpenGL rendering context. So we have imported our OpenGL rendering context by importing the OpenGL.gl library, and we should be very careful to call OpenGL entry point until the OpenGL context has been created, because failure might create very extreme behavior. We then go ahead and define our vertex shaders and fragment shaders, which I already explained what they do. And here in the shader variable, we are going to store the output of our shader.compile program, in which we pass our vertex shader and fragment shader. So the vertex shader and fragment shader can be defined here as you wish using different parameters, and they are passed in the compile program function and stored in the shader variable. Then we also have a VBO variable. So what does VBO stand for? VBO is vertex buffer data object. So modern OpenGL wants you to load your data onto your video card as much as possible. For geometric data, this is generally done via vertex buffer object. These are flexible data storage areas reserved on the card with various strategies available for streaming data in and out. So inside a vertex buffer object, you're going to define an array. This array is going to basically define your shapes, and those shapes are going to be rendered on your display. Then I have a render function which basically defines what shapes I want to render. Like I have a triangle here, and they basically use GL draw arrays function to draw the triangle. So that's about it for this basic code, which is just going to draw a 2D triangle and a square on my display. Okay. My file name is pyopengl basics, and there you go. As you can see on your screen, we have a green triangle and a green square that was rendered here using my render function, which used the VBO to calculate various things in the backend and show us our 2D shapes. Now let's get into the interesting 3D things. So for that, I'll show you my cube code for the code for drawing a cube. So this code not only draws a cube using wireframes, but it also rotates it using our rotate function. Where is my rotate function? I'll show you. Yeah, GL rotate F. So this is again inbuilt function in OpenGL library, and it is used to rotate your cube, and you have to pass the 4 parameters which tell the function how do you exactly want to rotate your cube. So the way we do this, okay, I'll go ahead and show you what output we exactly get for, so that you can see. So that is how your output looks like. You have a cube which rotates. You can see that after a brief amount of rotation, it is going to stop and do the same rotation back from the original position. That is because of the way we have defined our rotation function. So the way we draw this cube, we have a array of vertices, array of edges, and a function that joins those vertices and edges, GL vertex 3f v function. And in this code we have not directly used pyopengl, but we have used pygame, which is analogous to pyopengl in Python. So in pygame, the code becomes very easy as compared to this code, in which we had to pass some C code as comments. We directly have wrappers around that code, which make it easier for us to define shapes and vertices and edges and directly draw them on your display. So this pygame library is used as a wrapper around your pyopengl. Although it's not exactly pyopengl, it is used to make rendering easier on Python. So that's how I managed to draw a 3D cube right here. I'll close this window, put this down. Next we see how we deal with light and shaders using my light and shader code. Again, here you can see all the code that is there in brown or that orange color is C++ code, which we are passing as comments. It is huge code. So basically what we are doing is we are writing C++ code, but we are writing it in Python. That's exactly what's happening here, which is kind of a workaround that I could find, so that instead of working with C++, I could work with Python, since my C++ wasn't getting set up properly. So let's look at shaders now. So what we do here is we again do all the imports as usual before. pyopengl context, pyopengl.gl library, which is the backend OpenGL library that this Python code is using. Then in that we have our class. I've named it text context, which is going to test the context of your OpenGL code. So it is going to use OpenGL context at the backend, and it is a code that I've written so that I could demonstrate how I'm going to do shading of shapes. So after this shading is done, I can go ahead and draw a sphere. My sphere won't be a wireframe, but it will be a shaded sphere. So it will be a solid ball with some shading around the ball, which will make it look like a sphere. That's my motive behind demonstrating this shading code. So in this, before you look at the code, I would like to explain two things that we have here. Diffusion and ambient lighting. So what ambient lighting means is the lighting that will fall on your object, and ambient lighting is used to simulate the radiant effect in the lighting, that is the effect of light which is bouncing around. So the environment which otherwise isn't accounted for by your lighting model will be uh, shown by this ambient lighting uh, in your shaders. So that's what ambient lighting is used for. So if you look at the C++ OpenGL code, the legacy OpenGL, the ambient light was handled as a setting declaring each surface ambient reflectance. Reflectance is a color. Basically, the ambient lighting will look like a gradient of color on your shape. So any shape that you define, it will look like it has a gradient of colors, and that will make us feel as if it's reflecting some amount of light. So that's what ambient lighting is going to be used for. Then diffuse lighting is another concept. Diffuse lighting is used to simulate re-emission for a surface where the re-emittance isn't ordered. That is, the re-emittent light is diffused basically. So a non-shiny surface which re-emits everything that hits it. That's what it will show. So basically think of like something like snow or any rough wooden board, or like something similar to wood basically. That is what will diffuse light. So that will have a very high diffusion factor but a low ambient factor, because a wooden board won't reflect much light as something like a metal would, or let's say let's say a mirror would. So that's what diffusion is used for. So those two things are used here in my code. Again, we have the similar code where I am going to write the onInit function just like we had in the basics. So this onInit function will have something called as a Phong. So that Phong weight calculator is going to have my light position and what kind of geometry I'm going to use defined in it. So my light position is something very important when I talk about all things like ambience and diffusion, and that is what we define first. So in our vertex shader, we actually use the eye space forms of the two vectors for angular calculation. So let's go back to vertex shader. So right in this code, we're going to use the eye space forms. Then as you can see here, I've defined the light diffuse and light ambient variables, and then I have, so as you can clearly see, this is a C++ function, C++ codes, I'm sorry. And then we have a void main here like we have in C++, where we have all the OpenGL code inside it. We have a projection matrix, and that is going to be stored in GL position variable, and that's basically about it. So I'll show you the output. This all of this code which is defining VBO, all the vertices and all the shaders and everything, all of this amounts to a very plain simple output, and so you will appreciate the amount of code that goes on to writing all those big games. Look at that small white piece at the center with a little black at the ends and a little bit of white in the middle is all that we could render with this whole amount of code. So that basically helps us appreciate the um, efforts that designers have to take to design any kind of games and render any kind of shapes. So now, since we have understood shaders, I would like to go ahead and show you how my cube looks like. So my cube does very similar things. It basically uses this not my cube, my sphere, I mean my sphere does very similar things to our shaders. It uses shading in a very efficient way to fool you into thinking that a circle that was drawn at the center of the render is a sphere. So it is exact similar code. I have uh, on init function in which I'm going to define my Phong weight calculation function, which contains the light position, the geometry, and all those things related to initialization of our render. Then I have the shader function, which is going to initialize all the shading attributes, and then the compile shader function, which includes all the code that goes behind drawing the sphere. Then we have other code which is used to manipulate the coordinates of the sphere. So that goes right here. The radius of my sphere is 1 here. I can change the radius to have a bigger sphere, and we'll see that in a while. And then again, of course, I have my rendering function which uses everything after initialization to finally render my sphere. And all of this code here, which I did not exactly explain in my light PyOpenGL light code, the shader code, was basically using the GL uniform 4f function to pass inside it the ambient location ambient light location, the diffusion light location, and all the setups that we did here in the initialization to actually instantiate an object of our render. So rendering is basically actually instantiating our sphere and not the code above it. And of course, then we have the main function in which we call the class and call the context main loop of the class. So I'll go ahead and show you how the sphere looks like. So there you go, you can see the tiny sphere. All of this code, again, it's about 164 lines, was used just so that we could see the sphere. You can see if let's say if I can drag this, you can see the wireframes in fact of my sphere. They are very light, and that was not my objective. In fact, I wanted to show a solid circle with shades so that it looks like sphere, but in fact a render is also showing us the wireframes that went on to making this sphere. So that's what it looked like. Let me go back and change the radius. Where was my radius? Let's do Control F, radius. Let me make this 10 and then render again. In fact, I think it went out of bound. Yes, so 5 works, 10 went kind of out of bound. So when I keep the radius 5, you can see a big sphere. So now one thing if you noticed, my sphere now does not exactly look like a solid round object, but it looks like how many sides are these? 1 2 3 4 5 6, a 12-sided solid polygon instead of a nice round shape. But that's because we rendered a small sphere and then increased its radius to make it look bigger. So this is kind of like zooming into a small object, and um, we would get a bigger size sphere if we rendered a bigger size sphere, and not if we just increase the radius of the smaller size sphere. So that's why you can see this object as a solid polygon instead of a sphere. Maybe it's close enough, I would say. We have the shading on one side and we have the light coming from the right side. So that's how we have defined our lights in the initialization function. So that's about it. That's how I went on to create my OpenGL code for digital assignment 1, wherein I demonstrated how we draw basic shapes in OpenGL, how we draw a cube wire frame. In fact, I'll go ahead and show the cube wire frame again. That's how it was. Then I demonstrated how we do shading. That's right there. Left side is darker, right side is more darker, but center is light. And after we learnt all that, I demonstrated how we draw a sphere. So that's a sphere. It has all the shading elements. Light coming from right side, left side is darker. And that's all there is to basics of OpenGL. If you have any further doubts in this, I will be very keen on answering those questions. That's about it. Thank you.